Good morning, everyone. It is the lesson for Monday, June 28th, 2021. It says myself, Mr. McKeever, recording for your very first lesson of physics, which is fun. We're going to talk about the intro to physics, the basics of physics, and stuff like that. This lesson will be asynchronous, as well as the one on Wednesday, as you have two major exams in your biology class. So these two classes will be asynchronous. And as a reminder, there is no lesson for July 5th. July 5th is a holiday. Please take that day and enjoy it. I will remind you that as well in the next lesson. So with that said, and with the mess that I have set up in my office right now, so I'm building a computer, let's get into the fun. So we're going to talk about physics, science, force, mechanical equilibrium, and vectors today. So I often say that when you measure something, you can measure something, express it in numbers, you know something about it. When you cannot measure it, when you cannot express it in numbers, your knowledge is meager and unsatisfactory of kind. Maybe the beginning of knowledge, but you have scarcely your thoughts in advanced stages of science, wherever it may be. This is Lord Kelvin, who was the person that Kelvin temperature scale was named after. So he kind of laid it out saying that science is basically the measurement of everything, and how we measure that is via math. So about science, we can't control Earth's motion. We've learned the rules by which it moves. Study the nature's rules about what it's about. Understanding these rules add richness to the way we see our world. Contrary to our Congress's belief, and evidently a senator from Texas, we cannot change the trajectory of the Earth or the moon. And if we did, it would be extremely catastrophic, right? But we understand how it moves. Physics is about the basic nature of things, such as motion, forces, energy, matter, heat, sound, blah, blah, blah. The study of science branches into the study of living and non-living things. Living things include sciences like biology, zoology, botany. Physical science includes geology, right, which rocks, astronomy, chemistry, and physics. But you can't understand the other sciences, and you can understand the other sciences, but you can't really get a grasp of them without physics. Physics is the most basic of all the sciences. You know, chemistry is about how things are put together. Biology is about how more complex in matter stays alive, right? And then mathematics is kind of our language of science. It's the way the ideas of science are expressed in mathematical terms and makes them very unambiguous, right? With gravity, we know that items fall to the Earth at 9.8 meters per second. We have a mathematical formula for that, and we can calculate it, we can verify it, and we can duplicate it. The equations of science provide compact expressions of relationships between concepts, and the methods of mathematics and experimentation have led to several successes in science, including sitting here right now on Zoom. Person who says that it's only a theory likely doesn't understand the scientific method is a guess, a number of facts, or a vast synthesis of well-tested hypotheses and facts. I love it when people say this to me. I'm a real kind of staunch defender of the globe Earth theory. I didn't realize I had to say that, but there is a huge current movement stating that the Earth is flat, and we decided that thousands of years ago. Just saying. Or if nothing else, hundreds of years ago, right? But the big thing I always hear is, well, your science is just a theory. Well, good for it. A theory is different than what we use in everyday work, like everyday nomenclature, right? In science, it's a vastly experimentally verifiable body of knowledge. Vastly experimented, lots of experiments, body of knowledge, collection of knowledge. So yeah, my theory has proof. Scientific methods usually generally include some, if not all, the following: recognizing a problem, making an educated guess, a hypothesis about it, predicting the consequence of the hypothesis, performing experiments, and formulating the simplest general rules that organize the main ingredients, the hypothesis, prediction, and the experimental outcome all in one. The scientific method and attitude is one of inquiry, experimentation, and willingness to admit error. We've made changes to our science over the years. This is one of the things that makes people angry, because they think that science is just this is it. But in reality, science is ever changing. Use the COVID kind of pandemic as an example. At first, we thought masks weren't very effective. And on top of that, we also realized we needed masks for healthcare workers. There wasn't a large stockpile of masks, especially N95s. And so the CDC came out and said, for general people, masks are not important. After further research and study, it was found that masks are important in vector transmission. And they came out and they said, hey, look, we've done our research. We now know that masks are important. And people pointed, well, see, they were wrong. No, they weren't wrong. They just did more research. That's what's important about science. Scientific methods are extremely effective in gaining, organizing, and applying our new knowledge. Scientific method is often credited to Galileo and Bacon, are our two main scientists that kind of come back to that. Although the scientific method is popular, it's not the universal key to discoveries in sciences. Trial and error still happens, right? Think about Newton and the apple. That was trial and error. That wasn't a scientific experiment. And the success of science has more to do with the attitude of inquiry, experimentation, and humility than with a particular method. Scientists have to be very humble and understanding that they don't understand everything. If a scientist finds evidence that contradicts a hypothesis, law, or principle, then that law, principle, or hypothesis has to be changed. In science, a fact is a close agreement by competent observers who make a series of observations of the same phenomenon. Scientific hypothesis is an educated guess that is not fully accepted until demonstrated by experiment. When hypotheses about the relationship of natural quantities are tested or repeated and are not contradicted, they may become laws or principles or facts. Scientists must accept their findings even when they would like them to be different. I'm going to use an example in physical therapy right now. In physical therapy, one of the big kind of rage things over the past 2 or 3 years has been blood flow restriction. I have nothing personally against blood flow restriction, contrary to what everyone seems to think. But the only research out there shows that blood flow restriction is great for everything. That can't be the case. And if you look at all the case studies and all of the research that's out there on it, it all shows, well, this is fantastic. This is great. There are no side effects. There's no one that ever has any problems with it. I have a problem with that because every physical therapy treatment that exists, there has to be some counterintuitive treatments out there that doesn't work with. But there's no research on that type of stuff. So that's kind of upsets me about that because I think blood flow restriction is important for certain people. It can be useful. But I also like to know who it's not useful for so I don't hurt my patients. And that's the idea of science. We need to know both sides of it. Scientific theory is a synthesis of large body of information that encompasses well-tested and verified hypotheses, right? And theories of science evolve as they go through stages of redefinement and redefinition and refinement. There we go, I can speak. The refinement or changes to theories strengthens science, not weakens it. And more important than defending the beliefs is improving them, right? Better hypotheses are made by those who are honest in the face of experimental science. A scientific hypothesis must be testable. It is more important that they be aware of proving it wrong than there being a way of proving it correct. If I say that Brett Favre was the worst quarterback in the NFL, my problem is I have no way to prove that, either wrong or right. By what metrics? What is he the worst at? Blah, 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 right? Doesn't work that way. But I can say that, I can come up with a hypothesis where I say stone in red rock is primarily composed of red clay. Because I can then test and prove for that, or disprove it. Experiment is the test of truth in science. Here's a hypothesis that is scientific. No material object can travel faster than light. Even if it were supported by 1,000 other experiments, this hypothesis could be proven wrong by a single experiment. Therefore, we find it to be true, right? Right now, could we get warp speed in the future and prove this wrong? Sure. And then our science has to adapt. So here's some hypotheses that are not true. The alignment of the planets in the sky determines the best time for making decisions. No. Right? It cannot be proven wrong, nor can it be proven right. This is speculation. The hypothesis intelligent life exists on other planets somewhere in the universe can be proven correct, but there's no way to prove it wrong because no life has ever been found at this point. Right? Does that mean that we stop believing that there is alien life? No, but we just can't scientifically prove it yet. The hypothesis most people stop for red lights doesn't link up with our general understanding of nature, so it doesn't fit the structure of science, right? There was a movie back in the 80s called Starman where his comment was green light mean go, red light mean go faster. We know that here in Vegas all too well. Experiments are conducted to test scientific hypotheses. Science has to do with discovering facts in relationship between observable phenomena in nature and with establishing theories. Technology is our tools for doing that. Science and technology make up a large part of everyday lives, even more than before. Science and technology gave us stuff like this, right? Where we can have a mini computer in our pocket that's more powerful than we went to the moon with. A scientific way of thinking becomes vital to society as new facts are discovered and new ideas for caring for the planet are needed. Our planet's dying. We need new ideas. Science is mostly concerned with discovering and recording natural phenomena. The arts are concerned with the value of human interactions. They pertain to our senses. And religion is concerned with the source, purpose, and meaning of everything. I disagree slightly with this, but I'm not going to totally get on my soapbox about this because I think science also is concerned with the source, purpose, and meaning of everything. And I really think that science and religion are more closely aligned than they both like to think, especially when you consider the fact that one of the largest expenditures of the Catholic Church is in science, because most of the observatories in the world, including one of the ones down on Mount Lemmon in Arizona, are funded by the Catholic Church. Just saying, they're involved in science too. They're one of the largest contributors to the Large Hadron Collider in Switzerland. The domains of science, art, and religion are different, but they do overlap, right? Domains of science is natural order. Domain of religion often thought as nature's purpose or man's purpose in the world. But, you know, I'm not going to preach to you about religion or a religion because that would not be my place, although I'll interweave a little bit of that as we go along. The principal values of art and science are comparable. Literature describes a human experience. The arts do not necessarily give us experience, but they describe them to us, right? And you guys know this. You've had a visceral experience from some form of the arts, whether it's music, whether it's truly art on the wall, whether it's reading, right? It evokes potential within you, and it may evoke you to further your scientific knowledge sometimes, right? There are several books on neuroplasticity that have evoked lots of curiosity on my part. Science tells us what's possible in nature, and scientific knowledge helps us predict the possibility of nature even before those possibilities have been experienced. Progress in our age is much quicker than it was 1,000 years ago. I would agree with that, but of late, it seems like our progress has kind of slowed down a little bit, which I don't know is a bad thing, but it seems like it's artificially slowed down. I feel like, especially in our country here, we could advance a lot of our sciences faster than we actually are. And I think there's some roadblocks to that, excuse me. So the pyramids are a testify to human genius, endurance, and thirst for deeper understanding. How did the pyramids get built? Well, if you watch some shows on history, it's because aliens, right? But we don't know, right? How did they get, I mean, they are scientific marvels, especially something like Machu Picchu down in Peru. The blocks down there are cut with such precision that they'd be challenged to be cut today by today's technology. How did they do that? With just general tools. I don't know. It's amazing to me. A few centuries ago, cathedrals, synagogues, and temples and mosques were manifestations of people's visions. If you've never gotten a chance, and I highly recommend it if you haven't, travel to Europe and actually go on a tour of cathedrals in Europe. I lived in a town in Denmark called Haderslev. And in that town, they had a beautiful cathedral that I can't tell you how many times I visited just because the sheer awe of the building itself was amazing. right? So we have an enormous focus of human energy was inspired by a vision that went beyond world concerns, a vision of the cosmos. Today, the effort of many of our most skilled scientists, engineers, and artisans are directed towards building spaceships that orbit the Earth, right? We would have never thought of that 20 years ago, 40 years ago. Many people working on today's spaceships were alive before the first jetliner ever carried passengers. And so where will your younger lives lead in comparable time? What will physical therapy look like by the time you guys are in your 40s, 50s? It'd be different. So forces, let's talk about that really quick, right? This is not talking about John Force or the Force family that are in drag racing, although they apply to force. Things that are in balance with each other in the environment are illustrated in equilibrium, right? Things in mechanical equilibrium are stable without changes in motion. As I hold this ball here and it doesn't move, that ball is in mechanical equilibrium with my hand. Right? Rocks on the ground are in mechanical equilibrium because they don't move unless acted upon. An unbalanced force would be needed to change a resting state. A force is needed to change an object's state of motion, right? As I sit here with this ball won't roll unless I enact a force upon it. Force can be a push or a pull. Some kind is always needed to change the state of motion of an object. When you come to a rest with your car at a stop sign or a stoplight, in order to move forward, you have to enact a force on your vehicle by hitting the gas pedal. Force some kind is always required to change the state of motion of an object. The combination of all forces acting on an object is called the net force. The net force of an object changes its motion. So in the case of like a car, your car can be moved forward by hitting the gas. I'm going to use this weekend as a great example. For those of you that don't know, I'm a huge NASCAR fan. One of the people in NASCAR that's probably one of the most hated people in NASCAR right now is Kyle Busch. He won last night or yesterday. But he won despite the fact that his car was stuck in fourth gear. When he was pulling out of the pits, it was almost impossible to get that car started by just using the gas. So the engine was exerting a force on the car, but so were the people from his team that were pushing the car to get it moving. So the net force there got the car moving. The scientific unit of force is the Newton, abbreviated for N, for Sir Isaac Newton, the founder of Fig Newtons. Oh, that's not the way it works. The net force depends upon the magnitude and direction of the forces. Here we have two forces being applied to the right, the 15 and the 10 Newton force. That means the total net force acting on it is 15. If here we have 5 newtons left and 10 newtons right, we'd end up with a 5 Newton net force going to the right. If we have 5 newtons going one way and 5 newtons going the other, the net force would be 0, and this object's not going to move. So the net force is the total force acting upon an object. If someone came and shoved me to the right and someone came and shoved me to the left at the same time, depending upon how much force was enacted upon me, would depend upon which way I went and how much I could resist those forces. If you're holding a rock book ball, you're supporting it with support force that pushes upwards. So if I'm holding a ball here, this ball has a weight. As I'm holding it here, that weight is pushing down. My hand is technically pushing up, providing it with a support force. Because the object is at stable rest, if I'm just holding it here, right, the net force acting upon it is 0. So maybe being pulled down with 1 Newton, I'm pushing up with 1 Newton, but the net force is 0 because it's not moving. If you're holding a 1 kilogram book, you're required to exert a force upwards in order to resist that gravitational pull downwards. Usually, depending upon how you're holding that book, the force is applied by the biceps brachia, right? So if I'm holding the book out here in front of me, right, most of my force used to hold this book up is held by my elbow flexors, my biceps brachii. So tension and weight. A stretch spring is under a stretching force called tension, right? So tension is a stretch force. I want to grab something here as an example. Nope, that's not what I wanted to grab either. Huh. Don't know what I wanted to grab was. Let's figure that out. don't know where my TheraBand went to. I had a piece of TheraBand here I was going to use as an example, but I don't know where it went to right now. So anyway, stretching force, right? So something that's being pulled apart. Well, here I've got a hair tie. That'll work. Right? So this hair tie has a certain force that allows it to stretch. That's an elastic force. It's called tension. Pounds and newtons are units of weight, which are units of force. The upward tension of a string is same magnitude as the weight of a bag being pulled down. So if a string is holding a bag up like this, the upward tension, the tension pulling up, if I let go, boing, has to be equal to the weight of whatever it's holding here, or otherwise it'll either break or it'll pull down. So if a bag of sugar is tracked to Earth with a gravitational force of 2 pounds or 9 newtons, the upward tension of a string has to be equal. So here I've got a bag of sugar, right? That weighs 2 pounds. And I have a string holding it to a piece of plywood. As that bag of sugar is pulling down with 2 pounds of force, the string has to also equally be pulling up with 2 pounds of force for a net force of 0 in order for that bag to stay where it's at. If the force pulling down is greater than the force pulling up, the string will probably break. If the tension or the elasticity of the spring is greater than the 2 pounds of the bag, it'll pull it up some before it sets at a kind of resting equilibrium. So in that case, there are 2 different forces acting on the bag of sugar: gravity pulling down and tension pulling up. Force vectors are an arrow that represents the magnitude of a force and the direction of a quantity. A vector quantity needs both magnitude and direction. That means force is an example of a vector quantity. So a vector requires a force and a direction, versus a scalar, which can be described by a magnitude only and has no direction. Time, area, volume are all scalar quantities. So if I said something about temperature and I said that the temperature in my apartment right now was 76 degrees Fahrenheit, that would be a scalar. If I say that my temperature has increased by 4 degrees Fahrenheit, that would be a vector, because the vector has a direction. I've gone up by 4 degrees. So the vector at the bottom represents 60 newtons to the right. Typically, when I give you questions on your test, I'm either going to give you questions in the up, down, right, left category. But we can measure things by calling the east-west, north-south as well, superior-inferior, cephalid-caudal in the human body, lateral, medial, right? Internal, external, all of those are valid terms we use in the human body. So scalars are quantity numbers, vectors are quantity numbers of direction. When you come home to school, or drive to work, you could be driving 60 miles per hour. That would be a scalar, right? We'll discuss that as instantaneous speed later in this class. When you're driving on I-15, you could be driving 65 miles per hour north. Now that scalar would include a direction, so thusly it becomes a vector. This means you can change the object's state of motion by either changing the force applied to it or the direction it's going. Either of those changes the object's force applied. So mechanical equilibrium, which I talked about when stuff is not moving, can be expressed as the sum of all forces acting upon the object is 0. That's what that little symbol stands for. So this is the sum of all, right? You know, in a few years ago, they did a movie from Tom Clancy's books, which would be the sum of all fears. Okay, that was a corny joke, whatever. That stated sum is equal to 0 if the object is in mechanical equilibrium. This includes all forces acting upon the object. Up, down, left, right, AB, select, start. Mechanical equilibrium is a state where no physical changes occur. Whenever the net force on an object is 0, the object is said to be in mechanical equilibrium. This is known as the equilibrium rule or the equilibrium principle. If an object is at rest and has no exterior force is changing its motion, the object is considered to be at mechanical equilibrium. Use Mount Charleston as an example. Mount Charleston has a certain weight that is pulling the whole mountain down to the earth. At the same time, the earth is exerting a support force pushing that mountain upwards. Because those forces come out to be zero, Mount Charleston stays the way it is. What happens if Mount Charleston gets too much snow and has too much weight on it? Well, then the force acting downward is too great, and we get things like avalanches. For a suspended object at rest, the force acting upon the object must be balanced by the other forces pulling downward. So in the case of something where I'm holding it up like this, right? I'm suspending that object. There's a certain force pulling that ball down. I have to exert the same amount of force pulling it up in order to overcome it. Vector sums equal zero when objects are at mechanical equilibrium. So here I have a book sitting on a scale, right? Total weight of the book shows a weight of about 3.25 kilograms. So gravity pulls down at a rate of 10 newtons per kilogram. The book weighs 3.25 kilograms. So the book would be pulled to earth, right? So it's being pulled down to earth. There's a net force pulling downward at 32.5 newtons. In this picture, I'm holding the book up. If I'm holding the book up, that means I have to be exerting an equal amount of force of 32.5 newtons upward. At that point, the sum of all forces would be equal to zero. When I'm holding that book up, or when I'm holding this ball up, I'm exerting a certain force on that object. And as long as that object's not moving up or down, the sum of all forces is zero. Bridges are excellent examples of things being in mechanical equilibrium. This bridge looks like it's in perfect mechanical equilibrium, and we'd all like to cross it. They're designed with a structural maximum weight. I don't know what the maximum weight on this one is, but I'm guessing it's not as much as we'd hope it'd be going across it. And they're designed when the engineers must consider what would happen if that bridge was totally loaded, say with all tractor trailer trucks. What would happen if the structural support of the bridge was not able to exert an upward force equal to or greater than the vehicles on it? Well, the bridge would collapse. The bridge at left definitely looks like it's at mechanical equilibrium, and it is patent, right? But what happens when we put a force on it? Is it going to stay that way? We don't know. We have a lot of bridges in this country that are failing and eventually will cause catastrophic failures where we'll have cars falling into rivers, creeks, lakes, whatever it may be, if we don't take care of those bridges. Let's say you're hanging from Olympic rings and those rings are purely vertical. Your weight would be evenly distributed amongst each of those rings, and each ring would support your weight. So let's say we have a 100-pound person, and here's the rings, and they're perfectly vertical. Those are perfectly vertical lines. Don't call me out on that. And here we have a person hanging by those rings, and that person weighs 100 newtons. Each of these rings, the cables attached to them, are going to pull up with 50 newtons of force to overcome his 100 newtons of force being pulled down. If those angles are changed based upon either your right or left hand, those would reduce or increase the force required to support you. Those could theoretically cause catastrophic failures. So if instead I change one of these out to this side, that could increase the force needed on this one and maybe decrease the force needed on that one and cause a catastrophic failure over here. So think of the case of a bridge that starts swaying because of wind. At the point that it starts swaying, especially if it's one of those suspension bridges, those cables can be stressed beyond the effect of their force to be able to hold up, and it could cause catastrophic failure. For an object at rest on a horizontal surface, the support force must be equal to the object's weight. So what forces act upon a book laying at rest at the table? The one force pulling down is the gravity, the weight of the book. There must be an upward force acting on it to produce a net force of zero. So there's an upward force on the desk pushing upwards. The upward force balances the weight of the object on support. It's called the support force. A support force is often called a normal force in science. all of our floors have a normal force or a amount of force that can exert in order to push you up. Right? Have you ever been in an old house when you walk around the house and somebody's walking around, you can feel them walking through the house, right? That's possibly because that support force in that house is not as sturdy as it used to be. So here we have the same book from before, right? We've already determined that its force pulling down on the book is 32.5 newtons. That means the desk and equally the scale measuring the weight are acting on a 32.5 newtons force upward. What happens if the desk suddenly started exerting 35 newtons upward? Well, the book would float, start going upwards with the desk. Don't know that happen. Or if suddenly it couldn't support 32.5 newtons, the desk would collapse. That's why all desks and chairs have a certain force. The upward support force is positive and the downward support force is negative. The two forces add together mathematically to equal 0. The book lying on the table compresses the atoms in the table and they squeeze upward on the force. The compressed atoms produce a support force. So in the case of standing on a balance beam, how much force must the balance beam exert in order not to sag? Well, it has to be equal to your weight. Otherwise, the balance beam sags slightly. What would happen if you balanced yourself perfectly between two scales? The scale would equally demonstrate half your body weight. As it's split between the two, it would show half your weight. This can be useful when you're given a patient who's supposed to be partial weight-bearing status. If the doctor orders patient to be only 10% weight-bearing on their left lower extremity, and they weigh 100 kilograms, the patient will only be able to put, 10 kilograms of weight on that leg. You could use the support force demonstrated by the scale to show the patient how much force they're allowed to put on that foot. So if objects at rest with no movement are called static or mechanical equilibrium, we also have to have an object moving at a constant speed and a constant direction. And that is called dynamic equilibrium. So objects at rest are said to be in static equilibrium. Objects moving at a constant speed in a straight line path are said to be in dynamic equilibrium. State of rest is only one form of an equilibrium. So an object has to be moving at a constant speed or acceleration in a straight line path in order to be considered in dynamic equilibrium. Once in motion, if there's no net force changing the state of the motion, it's in equilibrium. So once that's gone. I don't know where that went to. Oh, there it is. Once I throw this ball, right, and it's going towards this other hand, once it reaches its maximum speed and it's traveling in a straight line, no other forces are acting upon it. So the net force acting upon this object is 0. It's in dynamic equilibrium until it hits my other hand. When it hits my other hand is going to enact a force to stop it, right? An object under the influence of only one force cannot be in equilibrium. So if there's only one force acting upon an object, then we can't do anything. So what is some of the forces acting upon this object? Well, the force that I'm pushing it and the air resistance going in the opposite direction, as well as gravity as well, right? If you push a desk across a room on floor sliders, when the push on the desk is same as the force of friction between the desk and the floor, the net force is 0 and the desk slides at an unchanging speed. If you increase the force to be greater than the friction force, you will accelerate. If you decrease the force, that'll be less than friction. Friction will eventually win, and you'll decelerate. Even though in physics, deceleration doesn't exist, it's just negative acceleration. I know that's a confusing thing that always got me in physics too. There is no such thing as deceleration in physics. If the desk moves at a steady, constant speed without change in motion, it is considered to be in dynamic equilibrium. Friction is a constant force between objects that slide or tend to slide against each other. In this case, the net force is 0 because friction and the force you're applying to the desk to move it equate out to one another. An airplane flies horizontally at a constant speed in a straight line direction. Its state of motion is unchanging. In other words, it is in equilibrium. Two horizontal forces act upon the plane. One is the thrust of the propellers as it pulls itself forward. The other is the force of air resistance that acts in the opposite direction. Which is greater? Well, if it's traveling at a steady speed in a similar direction, meaning north by northwest, northwest, whatever it may be, neither. Those forces are going to be equal, and the patient or the plane is going to be in dynamic equilibrium and not be moving forward or backwards at that point, technically in relation to where it is at that given moment. Is it going to be moving in relation to the Earth? Sure. But it's not accelerating or decelerating. So therefore, it is in dynamic equilibrium. Now, say the pilot suddenly juices it a little bit and gives a little bit more thrust. Then the plane's going to speed up. And for that point when it's speeding up, it is no longer in dynamic equilibrium until such time where it returns to a consistent speed at a consistent vector or direction. Then it goes back into dynamic equilibrium because, again, it's still moving, but at a steady pace. So back to these vectors. To find the resultant of two vectors, construct a parallelogram where the force and vectors are on adjacent sides. You are not going to have to calculate these for me. Just have to know the rules. The sum of two or more vectors is called the resultant vector. The combining of vectors is quite simple when they're in parallel. If they go in the same direction, they add. So if I have two forces going like this, one's 1 Newton, and I have one going for 2 Newtons, that means the resultant vector is 3 Newtons. If they go in opposite directions, so I have 4 Newtons going this way, 5 Newtons going that way, my resultant vector is 1 Newton going that way, because 4 minus 5 leaves me with 1. And they would be in relation to going to the right or the left. This goes back to the book example before. The force pushing down on the book is gravity. Force pushing up is the strength of, is the strength of either my biceps brachii or the desk providing the support force. The resultant vector would be non-existent. It's 0 because the book's not moving anywhere. So in that case, remember it's 32.5 Newtons, right? 32.5. Pulling down. My biceps are going 32.5 Newtons up. Newtons. That means my resultant force is 0. It's not going up or down because the book is just sitting at static equilibrium. So here's kind of looking at the parallelogram rule. To find the resultant of non-parallel vectors, we use the parallelogram rule. Consider two vectors at right angles to each other. The constructed parallelogram would be the resultant diagonal angle. What I want you to know about this is if you're drawing a parallelogram rule, and let's say my force up is 15 Newtons, and my force to the right is 5 Newtons. My resultant vector is going to be like this, but it's going to be skewed towards the larger force. So a resultant vector is always going to skew towards the larger force. If the forces are equal, if I've got a 5 Newton and a 5 Newton, that resultant vector is going to be right down the middle of it. But vectors and forces will always skew towards the larger force. Consider what would happen if you suspended a 10 Newton object midway along a very tight horizontal stretched guitar string. So here we have our guitar string. And we put a 10 Newton object here. Is it possible for the string to remain horizontal without a slight sag? Not a chance, not on a guitar string. 10 Newtons is too much, right? But eventually, the guitar string will sag and it will come to rest, hopefully, if it doesn't break. And then we can act upon the parallelogram rule to come up with a vector of force showing how it happens. All right, so that is it. So for the physics stuff, what I've done at the end of almost every physics lesson from now on is I've tried to put review questions that will help you study and practice for your quizzes. So those are there. I'm not going to go through these. These are for you to go through on your own. But I try to put those on there to help you review. And there's even some multiple choice questions that can help you review for your quizzes and your final in this class. With that being said, that's it for the intro to physics. I know I had loads of fun. I hope you had loads of fun too. I'm hoping that this is not going to be the most boring class you've had. I will try to keep it a little bit fun, keep the levity a little bit higher. I hope you all did well on your midterm today, and I hope you guys will do well on your test on Wednesday. I will see you Wednesday. Thanks a lot. Have a great day.